Hello, everyone. We are going to consider one example of partial differential equation from section 10.7, a string with free ends, which is not really a string because you cannot kind of vibrate a string with free ends, but something like a pipe where the air inside oscillates can work as a string with free ends, and that's actually like kind of musical instrument too, right? You can create something with two free ends. So I'm going to start with differential equations. So let's write it down. And again, my coefficients are mostly arbitrary. I just want to show you example of one problem where I solve it from the beginning to the end, okay? So you can have a general idea how everything is working if you do not split it into little parts. So uxx equals, sorry, not uxx, but for uxx equals utt. Here, u is a function of x and t. For the string, it describes deviation of the piece of a string from equilibrium. But if you consider something else, not a string, it can be a pressure, for example, can be something else. So in our case, we do have one space coordinate x and one time coordinate t, and there are second partial derivatives by x and second partial derivatives by t. Initial conditions, or like say first end conditions maybe. So y prime of 0t, 0 is x position, equals y prime of 4t equals 0. I'm going to put here free ends. Well, when you have fixed ends, something like this happens, right? Well, approximately. You fix ends and oscillations happen between these two fixed ends. When you have free ends, you can try to kind of play with a piece of rope and try to oscillate one side of it. You're going to see that if the end of the rope is not fixed, it's going to be something like this, create something like this. So it's going to look like it's fixed, but it's fixed like, let's say, in the position of farthest displacement from the equilibrium. So at this point, derivative is going to be equal to 0. These 2 points function is equal to 0, right? Fixed ends, but free ends are going to produce derivative equals to 0. Well, because nothing is stretching it on this side and nothing is stretching it on this side. So it's going to kind of be, nothing is bending it, and it's going to just be just flat. Okay. Okay. So now the rest of initial conditions. U derivative by t, and well, I put derivative here, but I did not specify which derivative. Here is going to be derivative actually by x. Maybe I should write actually x here instead of writing down the derivative sign. So, well, derivative is a little bit more clear for me, but you know, that's a first derivative by x, right? And the first derivative by t, for any x is going to be equal to 0. So initially nothing is moving. U of x 0, so initial conditions equals f of x. What does it mean? U of x 0. So at t equals 0, the string is displaced a certain way. For example, if you play a guitar, you can pull it a little bit off equilibrium position and kind of release, but you don't give it velocity, initial velocity. So initial velocity is equal to 0, but initial position is going to be changed. I'm going to give it as piecewise defined function, and it's going to be equal to 0 from 0 to 2, and that's going to be equal to 1 from 2 to 4. So the string has length from 0 to 4, I don't know, 4 meters, 4 inches, 4 units of some kind. So we set up the problem. So this is just a problem setup. Now, solution. Solution. First, we're going to start with assumption. Assume that, make it a little bit smaller. I think it's going to give us more like space to write down the equations. U of xt can be represented as a product of two functions, one which depends only on space variable and one which depends only on time variable. And I call them respectively. X is the one which depends on space variable, t is a time function. Okay, we are going to do the second derivative of this. We remember that for the product, we are going to find partial derivatives, right? So maybe I should do it. So ux is going to be x derivative by t. Well, again, for x, t is a constant, and I differentiate only by x, and x is a function of one variable. I can use derivative here. Before, I had to use a sign of partial derivative because there are two variables, right? Here is just one variable. X depends only on x. And uxx is going to be, well, you differentiate the second time. T is still going to work as a constant because it does not depend on x. Same with t, ut equals x, t prime. And again, I put prime here because t depends only on t, and utt is going to be x t second derivative. So now I take this 2 and put it back into equation, and I have 4x second derivative by t equals x t second derivative. I'm going to do separation of variables. So I'm going to move everything with x on one side and everything with y on another side. So I'm going to push 4 toward t. So I'm going to write it down. X second derivative over x dividing by x equals t second derivative over t and 1 over 4 in front. Well, again, just formal reasons. And I'm going to set it equal to a constant negative lambda using separation of variables method, and these two independent functions, and if they are equal to each other for all x and for all t, they must be equal to a constant. I'm using constant equals to negative lambda. Well, it's just arbitrary constant. You can put it negative or positive. Eventually, when you solve the problem, it's going to kind of come up either positive or negative, but when you set it up first, you can put minus in front, which is going to what? Give us two equations. Let me move a little bit here. I'm going to write down these two equations separately and then move down to solve them. So the first one is going to be second derivative of x plus lambda x equals to 0. So I'm kind of writing down that this one is equal to this. And the second one is going to be second derivative of t plus 4 lambda t equals to 0. So we got two separate equations for two different variables, and we are going to solve them separately. The connection between them is going to happen because of lambda, right? And I'm going to start with solving the first one. I'm going to solve x second derivative plus lambda x equals to 0. And before I do the solution, I'm going to set up my initial conditions and initial conditions here. Why do I say initial conditions? For x, if you kind of forget about t, we are going to have not initial conditions, but boundary conditions. X prime of 0 equals x prime of, well, I'm going to put 4 here because we already know that the period is like, not a period, but the length of the string is 4 and equals to 0. We know that ends are free, means that x prime equals on the 0 end and 4 end equals to 0. Well, this is typical second order differential equation, right? We solve it as with characteristic equation r squared plus lambda equals to 0, from where we can make a conclusion that r equals plus minus I lambda. How about I raise a little bit of this and kind of make it like more narrow and write down this one nicer. R equals plus minus I lambda, right? Why it's plus minus? Because if you move it on the right side, you're going to have negative lambda, and that's going to produce plus minus I lambda. Now I'm going to use my boundary conditions to find what is supposed to be lambda. So not for all lambdas it's going to work, right? I'm going to I'll need to differentiate my solution, but first let's write down the solution. So solution x of x equals C1 cosine of lambda x plus C2 sine of lambda x. I think it happened in chapter 3, where we kind of have two trigonometric solutions, no exponential part here. Right, and we are going to find C1 and C2, or basically we are not going to find them, but we are going to set a condition on lambda using our boundary conditions. Boundary So this is boundary conditions problem. Okay, so first we'll need to differentiate it. So derivative is going to be, because we need a derivative, is going to be what? C1 and cosine is going to give us sine of lambda x, and we'll need to have minus and lambda over here. We differentiate cosine. And for sine, that's going to be cosine. So we are going to have lambda C2 sine, not sine, cosine, sorry. Cosine of lambda x. Next step is going to substitute in boundary conditions. So x prime at 0. If I substitute 0, I'm going to have 0 for term number 1 because it's sine of 0, right? And the cosine is going to be equal to 1 at x equals 0. So I'm going to have just lambda C2. Because it's supposed to be equal to 0, and we don't want to have a trivial solution. If lambda equals to 0 here and here, that's going to give us just a constant solution. X of x equals constant. So we are going to assume that C2 equals to 0. Well, actually, we can't have lambda equals to 0. So maybe we should write down this possibility too. C2 equals to 0 or lambda equals to 0. Why not? It's going to give us some solution, so we need to kind of keep it in mind. Now, let's write it down. If lambda equals to 0, then second derivative, I'm trying to finish solution with lambda equals to 0. I said that it's going to be a constant, but we'll need to kind of, explain it, right? Second derivative is equal to 0. I just plugged in lambda equals to 0 into my equation. And I'm going to have x prime equals to C1, right? Well, if the second derivative equals to 0, then the first derivative is a constant. Let's substitute initial conditions. Initial conditions. I call them initial conditions, but actually they're boundary conditions, right? Okay, initial. X prime at 0 equals C1 equals 0. So C1 equals 0. Okay, good. So now we have equation x prime equals 0. Solution of this equation is going to be again a constant. Well, I'm going to label it just C. Is it going to be a solution? Yeah, guys. X equals constant, any number here is going to be a solution in case when lambda is equal to 0, because you set up lambda equals to 0, it's a second derivative equals to 0. If you take a constant, and plug it into this equation, differentiate it twice, of course, you're going to have 0 equals to 0, right? Is constant going to satisfy our boundary conditions? Yeah, it will. Because you take a constant and differentiate it once, you're going to get 0. And of course, this boundary condition and this boundary condition are going to be satisfied because they both are zeros. Okay? So that's going to be our solution number 1. By the way, it's included over here. If you set up lambda equals to 0, this one is going to be 0, and this one is going to be 1, and that's going to be a constant. But just to show you that it's going to work. So x equals a constant is a solution for lambda equals 0. So Okay, now case number 2. If lambda is not equal to 0, then C2 must be equal to 0, right? And we are going to continue substituting our boundary conditions. So then solution x prime of 4 is going to be, we already know that C2 equals to 0, so this term is equal to 0. So we just have this one and plug in 4 into it. Minus lambda C1 sine of 4 lambda. I plugged in 4 instead of x. Sorry. Made it smaller again. We already know that lambda is not equal to 0. By the way, guys, somewhere I started writing down lambda instead of a square root of lambda. I think over here. Sorry, my mistake. And I really don't know why I'm doing it. Just because it's supposed to be square root of lambda, right? Sorry, I'm fixing it because it was lambda over here, but if you kind of extract the square root, it's square root of lambda. I have to fix it everywhere. Give me a second, guys. Maybe I'll stop the video and fix it first and then go back. Okay, guys, I think I fixed square root of lambda everywhere where I'm missing it. So if you just, well, just one more place to fix it back, sorry. But if you see that it's somewhere does not written, maybe you just can add it yourself. I'm sorry. And I forgot to fix it here, but it's going to be just one place, square root of lambda. Very good, guys. We already know that lambda is not equal to 0. So we just kind of consider this case. If lambda is equal to 0, we go on this scenario and we get a constant solution. If, like, we have a product of 3 different factors, right? Square root of lambda, C2, and the sine. If C2 is equal to 0, we are going to have, like, for this solution, how it's C2? Supposed to be C1, actually. I think it was C1 initially, but I fixed it to C2. If C1 is equal to 0 and C2 is equal to 0, we are going to get a trivial solution, x equals 0, which is going to work for the problem, but it's not interesting. It means that nothing is moving. So I'm going to write down not equal to 0, non-trivial solution. So the only possibility for us to turn this derivative to 0 is to make the sign equal to 0, And that's what we are going to do. So sign is equal to 0 when the argument is like pi n, right? So I'm going to write it down. Sine of square root of lambda by 4 equals to 0. Where it equals to 0, let me draw the picture. Sine equals to 0 where? Here and here. So these 2 points, if this is y and this is x, are going to be what? The points can be described as formula theta equals pi n, like n equals 0 at this point, n equals 1, n equals 2, and so on, right? Kind of going. So I'm going to write it down. A square root of lambda multiplied by 4 equals pi n. We already considered case of lambda equals 0. So it's considered over here. I did it on purpose so we can refer to it and forget about like 0 value here. So n is not going to be equal to 0. N is going to be 1 and like bigger numbers. Okay. So n is going to be n equals 1, 2, 3 natural numbers. So very good. Now what lambda was unknown because it was arbitrary constant initially, right? So we are going to set up square root of lambda equals pi n over 4. Or let's say we can write down what is going to be the lambda itself, right? The lambda itself is a pi n over 4 squared. And then our solution is going to look like this. X of x. We already know that C2 equals to 0, so there is no cosine term. No sine term. Let me see. Actually, yeah, no sine. C2 equals to 0, no sine term. So we are going to have only cosine term, and that's going to be C1 cosine, and we're supposed to just copy square root of lambda, right? Pi n over 4x. Well, that's going to be a solution. And we are going to say that n here equals 1, 2, and so on. And if we set up n equals to 0, we are going to have solution which is going to look like a constant. Imagine that n equals to 0, so it's cosine of 0, which is equal to 1 and a constant. And we have this constant solution. So what I'm going to do, guys, I'm going to extend here the sequence from 0 to 1 to just 0 is going to fit into the same formula. Okay. We are going to use 0 here because, again, plug in 0, we're going to get this constant solution, and constant solution is actually a solution. Okay, very good. So we kind of solved the first part of the problem. Now let's move to the second part of the problem. And I'm sorry, guys, give me a second. So guys, my second equation is sitting over here. I wanted to scroll a little bit up to show you second equation, and let's start solving it. I'm going to kind of stretch the board again. So second equation is second derivative of t plus 4 lambda t equals to 0. Here lambda is not a constant, any arbitrary constant anymore. We already know that a lambda is actually pi n square over 4. Okay. So I'm going to start solving it and use my known lambda. So let me give me a second, guys. I'm going to manipulate a little bit my screen. So problem 2, t second derivative plus 4 lambda t equals to 0. Well, for this one, the characteristic equation is r squared plus 4 lambda equals to 0, which is going to give us solution r equals plus minus 2 square root of lambda, right? I. And solutions for t are going to be t of t. Well, again, two solutions, sine and cosine. Cosine of 2 square roots of lambda t plus C2 sine of 2 square roots of lambda t. Here C1 and C2 are different from the ones which we had before. What else? Guys, you understand why do we have this minus in front of lambda initially? Because it's going to give us nice sine and cosine solution, which are easy to turn into 0 at 2 points. If you have exponential solution can be 0 only at 1 point, right? The second point is always going to be something different. Okay, I'm going to write down what is going to supposed to be the derivative. So derivative t prime of t is going to be equal minus c1 2 square roots of lambda sine of 2 square roots of lambda t. I'm afraid that I will forget about the square root again. Plus 2 square root of lambda c2 cosine of 2 square roots of lambda t. What we do know, we know that t prime of 0 equals, well, just plug in 0 here. We are going to have what? 2 square roots of lambda. And 0 here is going to give us 0. And 0 here is going to turn cosine into 1. And we have 2 square root of lambda C2. Sorry. C2. We also know what is actually lambda. Why my board is just... Well, know that's the square root of lambda from the previous solution is pi n over 4. So we are trying to use our initial conditions. Remember that initial conditions on derivative are equal to 0. And we don't have, or we do have initial conditions on, let's say, the function, but function is complicated. We are going to start talking about it a little bit later. So if lambda equals to 0, then what? Second derivative. Remember, we kind of were including 0 here into this. So my n was n 0, 1, 2, and so on. I just need to know what is going to happen to t. T second derivative is equal to 0. So first derivative is equal to a constant. And because first derivative is equal to 0, I'll need to write it down somewhere, but okay. Let me show you where it's first derivative. First derivative sits over here, guys. The first derivative, no, not even here. Let me move it even, scroll it even down. The first derivative of x0 equals to 0. So at t equals 0, derivative of my solution must be equal to 0. Okay, okay. So the derivative is equal to 0, and it's supposed to be equal to 0 at any point at like just any, like t equals to 0, it's supposed to be equal to 0. Okay, from where we can make a conclusion. If t prime equals to 0, then t equals to a constant. And this constant is going to give just constant solution, like we had it with x. Okay. Now, if lambda is not equal to 0, you know, the possibilities, two possibilities for lambda, be equal to 0 or not be equal to 0. If lambda is not equal to 0, then C2 equals to 0. Well, because, sorry, I forgot to write down that it's supposed to be equal to 0. And C2 equals to 0, right? And then the derivative at t is going to be minus C1, 2 square roots of lambda multiplied by sine of 2 square roots of lambda t. Well, just I plugged in C2 equals to 0 into my derivative, right? Now, remember that for this is going to be like expression for the derivative, and if t equals to 0 here, well, derivative is going to be equal to 0. So we're fine with this one. This satisfies our initial condition that derivative is equal to 0. Let's write down our solution now. What is going to be u of xt, which is kind of, you know, x of x by t of t. Well, if I just multiply t solution and x solution, I'm going to have a constant, right? And t solution, well, I need to write down t solution somewhere, because this one is only the derivative, right? Let me continue over here. Then t of t is going to be C1 cosine of 2 square roots of lambda t. I'm sorry, I forgot to write down this. Okay, well, I'm going to, instead of C1, I'm just going to write down C. And then write down cosine of 2 square roots of lambda t. And solution for, that's solution for t, right? Solution for x sits over here. It's also a constant, which I'm going to combine into this one, c. So this c1 and this c1, I'm going to multiply them and rename them as new c. Cosine of lambda x, right? But this is going to be only solution which corresponds to one n. I'm going to write down n here, and here, and here, right? And here. And lambda is going to be, sorry, I forgot a square root again. This is going to be pi n over 4, the square root. So now, all these solutions, n of them, are going to satisfy my equation and my boundary conditions and my initial conditions. So all of them can solve, can be a solution, right? So I'm supposed to include all of them into general solution. That's what I'm going to do. I'm going to add all of them and write down general solution as like sum of them. So I'm going to write down sigma cn cosine of 2 square roots of lambda t. Do I have a cosine actually? Why do I have a cosine? Supposed to, does it have a Yes, a cosine here too. Cosine of square root of lambda x and goes from 0 to infinity. And I'm going to write down actual value for lambda. So sigma cn cosine of 2, and square root of lambda is what? Pi n over 4t cosine of pi n over 4x. Here we can cancel a little bit. We can cancel 2 and 4 and get more nicer solution. Okay, here n goes from 0, 1, 2, and so on. Well, basically, guys, we already found a general solution. We did not use one initial condition that describes how the string was displaced at the initial moment of time. Remember over here, let me make it small first and then kind of point at which one we did not use. We did not use this one. We used these two conditions when we were finding the lambda. We used this condition when we were dropping one c. We dropped c2 from t solution, but we never use this condition. That's what we are going to do. We are going to use it. I don't like that it makes ovals. Okay, so I'm going to scroll up and show you how to use this condition. Well, I did show it once, I think, but I'm just going to show it one more time. So last initial condition. Last initial conditions. Last initial condition is u of x0 was equal f of x. Well, in our case, if I plug in 0 instead of t over here, the cosine is going to turn into 1, and I'm going to just have a series cn cosine of pi n over 4x and goes from 0 to infinity. I'm going to separate C0 so you can recognize the series better. C0 here, and then Cn cosine of pi n over 4x and from 1 to infinity. If you, in your mind, substitute m instead of n over here, m here and m here, that's going to be cosine Fourier series. Right? So basically, the coefficients are cosine Fourier series representation for the function. So why don't we do representation for the function as cosine Fourier series and then match the coefficients? The free term from this function is going to be equal to this free term, and the coefficient of just the first cosine is going to be matching the coefficient of the first cosine. What is L here? L here equals 4, right? L here is half of the period, right? And we need to continue our function which way? We need to continue our function. Well, somehow my pen stopped working. I don't know what is the reason. Maybe I just, my screen got frozen. Guys, I'm sorry, I had a little interruption. I don't know what happened to my computer, but it got frozen for a couple of minutes. So L is equal to 4, and I'm going to calculate these coefficients. Yeah, normally, guys, we call these coefficients AM, right? But because we already started labeling them as C's, I'm going to continue labeling them as C. But actually, they are AM coefficients, right? So I'm going to do Cn. I'm going to put in parentheses AM actually. 2 over 4 integral from 0 to 4, and here my f of x multiplied by cosine of pi n over 4x dx. And again, I'm doing this because if I represent a function f of x through cosine Fourier series, I just can compare the coefficients and make them equal, and that's going to find the coefficients for my final solution. Okay. Now, what I'm going to have 1 over 2 and the integral of 2 to 4, 1 by cosine of pi n x over 4. Why does it happen? Well, guys, my function f of x is going to look like this. It's going to be kind of equal to 0 up to 2 and then jump to 1 over here, right? So it's going to be like empty circle here. Oh, I'm sorry, it doesn't look like empty circle, and that's 4. So dx, not very difficult to integrate again, even don't need to integrate by parts, right? Just a simple integral. So it's 1/2 sine of pi n x over 4 divided over pi n over 4, right? And substitutions are 2 and 4. Maybe not super nice substitutions, but let's do it. Okay, I'm going to move to the side, and I have 2 over pi n. I'm kind of simplifying this expression from denominator and numerator, and 4 is jumping up and canceling with 2, and I have in parentheses sine. If I plug in 4, I'm going to have just pi n, and if I plug in 2, I'm going to have sine of pi n over 2. Okay, now I just need to kind of decide what is going to happen. For sine pi n is equal to 0, right? We remember that that's numbers over here, and over here. For sine of pi n over 2, we are going to have slightly more complicated picture. Let me draw. Yeah. So if, well, we already separated n equals 0, so n equals 1. That's pi over 2 here, right? Which is going to give us 1. And then n equals 2 is going to give us pi, which is going to give us 0. N equals 3 is going to give us -1, and then 0 again. And then kind of we are going to have this like 4 values repeated. So I'm going to write down n equals 1. The coefficient is, sorry, 1. N equals 2, the coefficient is 0. N equals 3, the coefficient is again -1, and n equals 4, the coefficient is 0, and everything is going to be repeated. So I want to write it down at like nice form, like -1 to a certain power. So how do I do this? -1. If I just write it down to the power of n, it's going to give me alternation between like minus and +1, but I'll need to get some zeros. So what I'm going to do, guys, I'm going to write it down as a power of, well, I can just use odd powers, right? I'm going to write it down as n and just describe what is n. N equals 2m minus 1, odd number. Well, it's just like n equals, well, the first number here is going to be what? M equals 1, 2 minus 2, 1. Doesn't look like it's gonna give me minus. Yeah, there was a minus over here too. There's one more minus, right? I was thinking like I'm just trying to combine. Okay, if we have one more minus from this one, we're going to have it actually like supposed to be minus in front of the whole thing. This one. So it's -1, 0, 1, and so on. So we have like, if -1 to the first power is going to be -1, then -1 to the second power is, not second, the third power is going to be -1. And the fifth power is going to be -1 again. Well, it doesn't work actually. I'm trying to figure out how to write down the coefficients. But that's the way I'm writing it out. Sorry. I'm going to write, I'm supposed to write down m over here. That's going to be the way to write it. Sorry, guys. Okay, so what is going to happen? We do have alternation, right? But this is alternation only inside of odd numbers. I don't know. I think I'm tired already and that's why I'm doing the stupid mistakes. We have alternation only within odd numbers, right? Even numbers are just going to produce zero coefficients. This is going to be zero and this is going to be zero. So we are going to have only odd numbers. To write down odd number, we can write it down like n equals 2m minus 1, when m is a new natural number. M is like 1, 2, 3. If you just plug in here 1, for example, you're going to have 2 multiplied by 1, which is 2 minus 1 is 1, right? So n equals 1. And then next one is going to be 2. 2 by 2 is 4, minus 1 is 3. So next one is going to be 3, right? And if you take this m, that's going to give you normal alternation. Like if you plug in 1 here, this m, it's going to produce minus 1. Remember, this 1 and this minus is supposed to be minus 1. If you take 2, plug in here, it's going to produce plus 1. And because there was a minus from this one, it's going to be minus. Now, kind of, we can write it down as a full formula. So 2 over pi, and instead of n, I'm going to write down 2m minus 1, just describing only odd numbers. And I'm going to write down minus 1 to the power of m over here, just as like alternation of the sign. And I think that's going to be my final answer. And here I'm going to again emphasize that m is 1, 2, 3, and so on. Now I just need the last coefficient C0. And C0 is 2 over 4, and I'll need to do the integral of the function. I'm going to right away do 2 to 4 because from 0 to 2 is 0, it's 1 dx, and that's going to give us 2 over 4 multiplied by 4 minus 2, which is going to give me 1 more 2, and that's going to be equal to 1. So now I'm ready to finish my function. U of x0 is going to be 1 over 2 plus sigma. I need to look back what I have. Okay, 2 minus 1 to the power of m divided over pi 2m minus 1, and the cosine of pi 2m minus 1 x over 4. Okay, these are the coefficients, like m here is 1 to infinity. Okay, so again, not all cosines are going to be here, only cosines for odd ends, and this formula represents odd ends. Now I'm going to write down the final solution, right? So these are going to produce the coefficients for the final solution too. No, I don't like the circle. So I'm going to write it down. U of xt is going to be my Cn, right? U of xt is going to be 1 over 2. No, let me move it below xt. It's going to be 1 over 2 plus, well, basically I'm just going to copy this and add another cosine here. 2 negative 1 to the power of m over pi 2m minus 1, the cosine of pi 2m minus 1x over 4. Why do you have x actually? Oh, no, yeah, the x is correct. Another one is going to be t, cosine, and here pi 2m minus 1 over 2t. Remember, with t we had it like doubled because it was a 4 initially, and that square root of 4 is 2, so we have like divided over 2. And we are done. We found all the coefficients. We finished the problem. So my final solution is going to look like this. So we are going to have oscillations in space and in time, and the coefficient is going to look like this, and there's going to be a constant solution. We are done. And I think that's the end of this example. Okay, guys, thank you for your attention, and I'm sorry that I confused myself over here because, like, I don't know, first minus confused me a little bit. Second, I was trying to write down in terms of n instead of like moving to a different number n. Okay, that's all for this example, and